I give you Lander Brandt from Meta, which is not Facebook.
Thank you, Jessica. Sweet. I'm excited to be here and share some tribal knowledge I built up over the couple of years of using ASAN, writing fuzzers, etc. So a little bit about myself. This slide called for a photo, so that's my cat, Vispy. But I'm a security engineer at Meta. I do a lot of code review, write a lot of fuzzers, try to break code, and one tool I really rely on a lot is ASAN. And so for those of you who don't know what ASAN is, give a quick primer on it. It's essentially a tool used for native applications to try to find memory safety issues. So if it finds something where, let's say you overwrite memory, do buffer overflow, read invalid memory, it'll give you a report like this. And how it works is it basically maintains metadata describing addressable memory ranges in the application. So in this example here, I've got an arrow pointing to this memory dump where whatever we're trying to read from, there's a 6 there in the brackets, and that means that only 6 bytes at that address are marked as addressable, and the things to the right are marked as F9, which is part of the global red zone, aka not addressable bytes. It has 2 components. The first component is the Runtime Library, which has some memory management hooks for malloc and free. So these are actually used for building the shadow mapping. So every time you make a new allocation, it's going to record the size and where the allocation is. Every time you free something, it'll mark that as freed and do cleanup state, whatever. It also has functions for checking if memory is poisoned. So when you do accesses on certain memory ranges, it's going to call into the runtime library to say, hey, can I actually read this memory? And if not, it'll dump some errors out. And finally, it has hooks for some common memory manipulation functions like string copy, memcopy, etc., for optimizations and some other internal stuff. The second piece is compiler instrumentation. So ASAN doesn't lean on this too much compared to some other things, but the instrumentation is mostly used to insert calls into the runtime library for, like I said before, just checking to see if a memory range is valid. And so the instrumentation, it really only instruments interesting loads and stores. And when it does this, it injects calls to these functions. So ASAN load 1 when you're loading 1 byte from memory, load 2 for 16 bits, 8 for 64, and so on and so forth. This is what it looks like under the hood. So load n is literally I'm trying to load memory from an address of a random size, could be arbitrarily large. This is actually from the ASAN code, so it just does a check to see if the memory range is poisoned, and if so, reports an error like I showed earlier. And this brings me to the main part of the talk, is you are probably missing out-of-bounds reads and writes in C, C++, Rust, whatever you're actually using ASAN with, if you are using certain programming patterns. So the first one I'm going to address is string containers. This is an example I came up with that we allocate a standard string object with a test string of 4, which is 4 characters. I then allocate a temp buffer, which is zeroed out, that has 10 bytes, and then I memcopy 10 bytes from the test string into the temp buffer and print out its contents. This should crash. I'm trying to read 10 bytes from 4, but it doesn't. And you can see here I'm actually running ASAN and I'm printing out null bytes. Why is this? If I just allocate a string without any data in it, the capacity is 15. And this is because of some string container optimizations. This is actually the code from libc++, which is really ugly and terrible to read on a slide. So I rewrote it here. This is not actually what its string looks like under the hood, but basically they have an inline storage buffer of 15 bytes for if you have a small enough string, they don't want to make a heap allocation. So if you allocate a string, and like I said, small enough, like just the string 4, it's going to store it in this fixed size buffer, which ASAN considers as valid memory. And it certainly is. This is legit memory that has been allocated, whether you're allocating a string on the heap, on the stack, whatever. And yeah, so the next container that's affected by this too is also vectors. So vectors work very similarly to strings where they have a heap allocation under the hood. And one really interesting thing about vectors is it has an exponential growth. So every time you reach the capacity, it's going to double the size by 2. So in this case, I'm generating some data from my fuzzer. I'm just pushing a byte every time. I'm returning that back. You can imagine maybe in your fuzzer, you're generating data piecemeal where you have a header and then the body or something like that. You're probably going to be growing the vector as you're pushing data to it. In that last example, if I were to print out the size and the capacity, the size of that vector would be 5, the capacity is 8. So there's a delta of 3 bytes. Very similar to the string example where I had 4 bytes, but there's an optimization for up to 15. There's unused space in here. And this is what I was describing earlier, the strategy for growing a vector. So when you reach 2 elements in a vector, it's going to double the size to 4, 4 to 16, so on and so forth. So basically the summary here is you have dead space that's unused that ASAN doesn't know about. That memory is allocated, it is valid, but ASAN doesn't know that this container is not actually using it. And so how do you fix these issues? This is the one weird trick. You literally just add standard library equals libc C++. There's some downsides to this. Like this actually doesn't fix that string issue, but this actually gives you container enlightenment for vectors in your target. And this will fix the issue I was just describing with vectors at least. It does actually have a side effect though of a changing layout for certain things, but here's that same example I showed earlier where I have a small vector with some data allocated in it, copy it to a fixed size 8-byte test buffer, and I'll run it, and we'll see that without this flag that I was just describing, it doesn't crash. I would have missed an out of bounds read here if I actually didn't give it the standard library equals libc++. With the flag, it actually has a proper heap overflow. I'm reading out of bounds, all's good. This is actually what it looks like under the hood with the annotation. So for some reason, I legitimately don't know why. Explicitly giving it the standard library enables this, this part of the code down here, or sorry, up here. You can see there's a preprocessor definition in, this is LLVM's or Clang's C++ library called annotate contiguous container. And for some reason, explicitly providing the standard library will enable this function, which under the hood, whenever the vector does a resize operation or clearing, something like that, it'll tell ASAN like, hey, I have 30 bytes allocated, but I'm only using 20, something like that. If for some reason you can't use that flag, so for instance, you may have black box libraries that you can't recompile, and so you may hit issues with like, your black box libraries not having the ASAN enlightenment and your own libraries having it, causing false positives. You could also just do a generic code level fix. So here, ASAN actually has an interface that you can import into your code where you can just calculate the pointer to this extra data in your buffer, get its size, and then manually call this macro called ASAN poison memory region. And you're giving it exactly like I just said, an address and a size to say, hey, mark this as non-addressable so I crash every time I read or write here. Or if for some reason you don't want to do that, you could just pre-allocate the size you need and copy the data into that. Exactly what the sample code does down here. It allocates a vector with the size of the data that you had previously generated, and then just copies it along. And then does an assertion to make sure, hey, everything's good. And this is one other trick that I like to mention that I picked up is if you have a safe abstraction that, like a span class or something like that, where it's meant to be a safe wrapper around a pointer and a size, whenever you're constructing that, I would personally consider it a bug if I ever constructed a span that had non-addressable bytes. Doesn't matter if my application is actually going to be reading from that memory or not. Like let's say the parser is totally fine. If I'm giving this thing invalid data, I just want to fail fast. And that's exactly what this does here. You can gate this behind, there's like certain checks you can do to see if ASAN is actually enabled. But this function here, ASAN region is poisoned, is basically what ASAN calls under the hood to see, hey, is this pointer in size, is that addressable? And if it is, I just assert false and crash. So in summary, the main takeaway from this is when you're working with manual memory management or containers that do stuff under the hood to manage memory for you, be wary of if it's actually enlightening your security tools to help it catch safety issues faster, or just poison your unused memory. Also, if you have your own allocators, so pool allocators or something like that, let's say you're working on a video game or something that you want to minimize the amount of heap allocations you do, enlighten it to know about ASAN, make it ASAN aware to ensure that you're actually catching these sorts of issues early on. And that's it. Thank you.